Showcase, which is hosted by NYSERDA's Empire Building Challenge. The purpose of these webinars, of this webinar series, is to help to familiarize you with technologies and strategies that can support and facilitate your decarbonization work, and more generally decarbonizing New York State's building stock. All of our sessions are recorded and we are posting them in an ongoing fashion on the EBC Showcase series website. Each presentation is about 20 minutes long, followed by a 10-minute Q&A in which the presenter will respond to your questions. Feel free to put those questions in the webinar chat throughout the webinar or after the presentation, and we'll be sure to get to them. And now it is my pleasure to introduce you to Bruce Lindsay of Trane Technologies. Bruce, take it away.
Great, thank you very much. Thank you to everyone at NYSERDA for inviting me to speak to you about a subject I love, decarbonization. And before I jump in, just a little background on myself. I'm with Trane Technologies. I head up our thermal storage business development group. I've been with Trane now for 3.5 years, but I've been working with Trane and CalMac for the past 35 years. I used to be with a little company called EPRI, Electric Power Research Institute, and I was executive director of EPRI's Thermal Storage Research Center at the University of Wisconsin. So I've been in the thermal storage business for a long time. That said, 3 years ago, it'll be in August, they passed the Inflation Reduction Act of 2022, and overnight, thermal energy storage systems qualified for a 40 to 50% tax credit. That changes everything. In fact, that's my new buzzword. It's a game changer. Next slide, please. So what we're going to try and do today, I'm trying to get 2 things done. I'm going to talk to you about the Inflation Reduction Act and how that makes thermal energy storage the most cost-effective way to cool a building for the summertime. And then I'm going to do a pivot and talk about using ice storage tanks to heat a building. This is all brand new. It's really exciting, and NYSERDA has already come to the forefront and has been championing this whole concept. We're calling it heating with ice. So that said, next slide. So real quick, what's happening in the utility industry today? Well, it's going through a major transformation. We're going from fossil fuels to renewable energy. And the problem with renewable energy is it's intermittent, meaning the sun doesn't always shine, the wind doesn't always blow, and there will likely be shortages. I personally don't worry about shortages. I think there's so many fixes around them. I'm more concerned with surpluses. There are times of the year where there won't be sufficient load on the grid to take all of the renewable energy that's being produced. And if you can't find a place to store it or use it, the grid's going to melt. That's overly simplified, but we're going to have some problems. So we need to have battery storage, and there are 2 types. There are electric batteries, and there are thermal batteries. And we're going to spend some time on that. On the next slide, please. For those who aren't familiar, this is a thermal storage system or a thermal battery. And it consists of a chiller on the left, a bunch of ice tanks in the middle, and glycol pumps and controls in the foreground. Real quick, this has been around now for over 40 years. We're putting water in those ice tanks. Inside, we circulate a water glycol mixture through some tiny pipes that will freeze the water solid. We typically freeze the water at night using cheap electric power. And then during the day, we melt the ice and use that to cool the building and not run the chiller during the very expensive peak periods. This has been very, very effective. It's been supported extensively by the utility industry with rebates. Some of those rebates have been going away, but we're seeing some of them come back to support electric batteries and electric vehicles. The nice thing is the Inflation Reduction Act now provides the thermal batteries with a simple 40% rebate throughout the United States, and we're looking at Canada's trying to go with a 30%. Next slide. Okay, for years, the federal government has been subsidizing solar, wind, geothermal, and electric vehicles with a tax credit, a 30% tax credit. That was scheduled to expire in 2023, and the Inflation Reduction Act extended that for 10 years. Additionally, it added batteries or energy storage devices to that tax credit list, and those batteries now qualify for a 30% tax credit. And if they're made in the United States, they get a 40% tax credit. And if the project is located in an energy community, you could get as much as 50% of the project is paid for. Almost all of the thermal energy storage systems are made in the United States. They basically all qualify for the 40%. A couple of things to talk about. It's for the entire system, although there's some changing in the IRS that we may not be able to get all of the system qualify for a 40% tax credit, 50% tax credit, and I'll try and talk about that shortly. One of the provisions in here is that you must use prevailing wage and apprenticeship program in order to get the entire tax credit. If you don't use prevailing wage, you only get 6%. If you use prevailing wage and apprenticeship programs, there's a multiplier of 5 plus your U.S. content and your energy community, adding 2% multiplied by 5. The real kicker, and this is really important for all of us, is in the past, a tax-exempt organization did not qualify for a tax credit. You have to pay taxes to get a tax credit back. Well, they changed the rules. Basically, K through 12, local government, state government can now get paid directly by the IRS, and it's a relatively painless process. And in addition, these tax credits can be stacked with utility rebates. Next slide. This is the basic form you fill out to get the money from the government. It's a form 3468, it's 13 and a half pages. Next slide. Form 3468 specifically calls out thermal energy storage and says we're going to treat it as a system. However, there are two systems. There's an HVAC system and a thermal energy storage system. As long as they're separated, no problem. The thermal storage qualifies for a 40 to 50% tax credit. However, if they're mixed, we get into a fun issue with the IRS. Next slide. So we were working with the IRS Section 48 investment tax credit for the past 2 years. That has now been replaced effective January 1 of 2025 with a Section 48 capital E clean energy investment tax credit. And thermal storage still qualifies for a 40 to 50% tax credit. The only issue is if the chiller makes ice exclusively, then the chiller qualifies for that 40% tax credit. If the chiller makes chilled water and ice, it's considered part of the HVAC system and doesn't get the tax credit. That's going to have an impact on the economics, and I'm not going to go into detail yet how we'll get around that, but we will. Next slide. So how have we traditionally sold thermal storage systems? Really simple. We go after unoccupied buildings at night. We're going to use the chiller plant to make ice at night. During the night, we make ice. During the day, people come into the building, they turn on the lights, turn on the computers, turn on the AC, and the electric meter screams like crazy. And most of those are pretty flat loads, but the chiller plant continues to grow as the day goes on. It gets warmer and warmer outside. So the chiller plant will be roughly 40% of the peak load. So instead of doing that, we make ice at night, and we melt the ice during the day, and we can turn off one or two or all of the chillers. If we turn off one or two chillers, it's called partial storage. We turn off all of them during the peak period. That's a full storage. Real quick, you can see the slides down below. That's one of our biggest ice storage projects at the University of Arizona. Those tanks are sitting out in the Arizona desert. And believe it or not, they're so well insulated, they only lose 1% of their charge per day. And the key takeaway here is you can put them in the buildings, outside the buildings, you can partially bury them, and you can rack and stack them. Next slide, please. We're going to look at a quick example of the economics. I'm looking at a middle school in Florida, $13 demand charge, 8 cents on peak, 5 cents off peak. Next slide, please. So this is for a particle storage system. This is the cheapest way to incorporate thermal storage. We're going to use the chiller to make water during the day. We're going to make ice at night and use that ice to supplement the chiller. That enables me to download the system. I go from a 600-ton chiller to a 330-ton, but I have to put in a bunch of tanks. Next slide. I should have done this. The little black dots is the chiller load. The blue is the chiller operating, making water. The purple is ice melting, and the green is making the ice. In this case, we want to get off the peak load from 1 to 6 p.m. And so we need a bigger chiller, a lot more ice storage. And as you can see, it's still smaller than the conventional system. Let's talk about dollars. Next slide. A conventional system for a 600-ton load would be 2 300-ton air-cooled chillers. That's going to cost roughly $900,000, and the utility cost will be about $130,000 per year. If they go over to partial storage, that's my cheapest option using storage. I downsize my chiller, but I add a bunch of tanks. I have a premium of $95,000, but I'm saving roughly $46,000 a year. That's a 2-year payback. That's not bad. Go to full storage. I want to get off that peak load, maximum savings, so I can save close to, what is that, $90,000 a year, but my payback is 5 years. These are both still viable. Okay, next slide. Here's the magic. You add a 40% tax credit, and in the case of partial storage, you get $400,000 back. It is, without question, the lowest cost option. Go to full storage, you get $554,000 back. It's way under budget. The question I'd have for any of you guys is, what would you recommend to a customer? The one with the best payback or the one with the most flexibility? I think you're going to figure out where I'm coming from. The full storage gives you maximum flexibility to deal with whatever happens in the utility industry going down. Next slide. And this just shows what happens if you can add in some utility rebates. This is in Florida, very, very lucrative rebates down there. And you can see this is a game changer. Okay, without question, full storage is the way to go. Next slide. I'm going to skip this one. And I'm going to skip this one. So what I've been talking about up to this point is talking about using ice storage to reduce your peak demand in the summertime. Okay, let's pivot. Let's change the subject here. Let's talk about decarbonization. How are we going to get rid of gas boilers? No more CO2 emissions. And this is the kicker, how do we avoid having to use electric resistance heat? That's going to be a problem. Well, we have a system which we're calling a storage source heat pump. We're calling it heating with ice. Next slide, please. This is a new concept. We don't want to use a chiller and boiler anymore. We want to use a heat pump, and a heat pump with storage. That is going to be your most cost-effective system you can put out there. Unfortunately, an air source heat pump is limited in its ability to heat buildings when it's really cold outside. And in most of New York, it's really cold in the winter, and you would probably need to have electric resistance heat with your heat pumps. Okay, we have a solution. We slip in what we call our chiller heaters or heat recovery chillers, and we're going to make ice in the winter at 6 in the morning, and we're going to generate 125 degrees of hot water. I'll go into more details shortly here. Next slide. We want to get rid of gas boilers in cold urban cities. Obviously, New York's the key market right now. And so it's really easy. Just rip out the gas boilers and put an electric boiler in. If you do that, you're going to have a world of hurt. Couple things. One, you may not have sufficient electric capacity for heating the building electrically. Two, if all of your neighbors decide to do that, you may have to put in a new utility substation, which is incredibly expensive and a long lead time. And obviously, everyone putting electric heat is going to exacerbate your winter peak demand. Okay. Good solution would be let's put some ground source heat pumps in. They're very efficient and that'll work well. Unfortunately, I don't think you want to put a ground source heat pump where you have underground infrastructure like subways. Okay, it's going to be difficult and they're very expensive. By default, you're going to have to go with an air source heat pump. Okay, but again, those air source heat pumps are limited in how low they can go, typically 0 degrees. And then even worse, in these urban environments, those tall, skinny buildings don't have much roof space where we can put air source heat pumps. We're going to solve that by using thermal storage. Next slide. Same thing. This is an ice storage facility in Manhattan. We actually have more ice storage tanks in Manhattan than anywhere else in the world. And people say, that's insane. That's the most expensive real estate in the world. Why would you use up that space for an ice tank? Well, Con Ed was in a world of hurt and they needed to reduce summer peak demand. They heavily subsidized ice storage systems in Manhattan. Real interesting. The tank is 8 feet in diameter. It's 8.5 feet high, and it holds roughly 14,000 pounds of water. When we freeze that water, we have to extract 144 BTUs per pound. It goes from 32-degree water to 32-degree ice. And that latent heat of fusion, 144 BTUs per pound, times 14,000 pounds, each tank can supply 2 million BTUs of heat. Okay, and you have a lot of these tanks in some of these buildings. It's going to be incredibly impressive. Just remember, there's always a lot of stored energy in the cold water in those tanks. Next slide. I'm going to pass this one. We can go back if the questions arise. Here's the real beauty that I'm going to talk about. What you see here is an operation map for a heat pump in a heating mode. At 95 degrees ambient temperature, we can supply 140-degree hot water to the building. As the ambient temperature drops down to 47 degrees, at 47, we start to see a derating, a capacity loss. And as you go all the way down to 0 degrees, you can see you can only produce 90-degree water. That might be useful, but that's awful challenging on existing buildings. What's really interesting for us is, if we go back, I'm using my water in the tanks as a source of heat. So if I look at 32 degrees, go all the way up and see where it intersects that line, you can see I can produce 125 degrees of hot water. That's the key here. We're making ice in the winter to make hot water. I should mention that we have other heat pumps that are using different refrigerants. This is using R54B. We have other ones that can actually produce up to 165-degree hot water. However, they're a lot more expensive. Next question, next slide. I'm not going to go much detail other than say that this is a trick. If I have to size my system for my peak hourly load, I need to put in 10 of these monster heat pumps on the roof. But if I can go with thermal storage, I can size for the average, and all I need is 5 of these units. So this is critical for the success of these systems. Yes, you have to add tanks with these systems. You have to find the space for them, but there's always a lot more space in a building for tanks. There's no more space on the roof. Next slide. There are only 3 major components out here that we're working with. Obviously, we're looking at the tanks, we're looking at the air source heat pump, and we're looking at the chiller heater. We've been making these now, the chiller heaters for, I'll say 50 years, the tanks for 40, and the air source heat pumps, 20 years in, 40 years in Europe, 20 years in the United States. We know how to design, manufacture, install, service, repair. There's very little technical risk here. Only issue is we got to think about how we're going to control these beasts. Next slide. I'm going to skip this one. This is a fun one. I should have shown this a little earlier, but we're looking at two different electric grids. We're looking at the grid in Chicago, we're looking at the grid in Buffalo. Okay, Chicago is a pretty dirty grid. Buffalo, it's almost all hydro and nuclear, very clean. If I rip out a gas boiler and put in an electric boiler, I actually increase the greenhouse gas emissions by almost a factor of 2. People don't realize that that can happen. You go down to Buffalo, and we rip out the gas heat, put electric heat, it stays the same. Have you decarbonized? Not really. If you go to a heat pump, significant reductions, okay, on both, but there's still a lot of greenhouse gas going off. If you use a storage source heat pump, we can actually obtain an additional 26% savings in the greenhouse gas. We get down to, we basically cut it in half. Next slide.
Will do. And then if you, I don't know how many slides you have left, Bruce, but if you want to wrap up so we have a few minutes for questions, that'd be great.
Okay, that's what I want to do. We've got, I said we had to get some controls. We actually installed our first unit in La Crosse. It's been up and running now for 2 winters, and we're very excited about it. We're trying to get people to go out and take a look at it. Next slide. You can see the performance of that unit over the past 2 years. The little red dots are the COP. We're seeing a COP basically greater than 2.2, twice as efficient as an electric boiler. Next slide. This is the one I really been wanting to talk about. This is something that you guys should all take a bow for. This is 55 Water Street in Manhattan. Okay, Manhattan, New York, has some really aggressive rules regarding carbon dioxide. You cannot use natural gas in new buildings over 25,000 square feet. Local law imposes a building performance standard, basically a greenhouse gas cap, which will fine you millions of dollars. And this particular building is the largest building in the state of New York, 3.8 million square feet. We put ice storage in this system in 2012, 2013. We are now using those existing tanks to heat this building. This was installed prior to January of this year. It's been up and running. So far, they've avoided $1.2 million in fines. They've been able to reduce their steam consumption by 70%. They are ecstatic. It received funding from NYSERDA for the engineering. It received rebates from Con Ed and qualified for a 40% tax credit. The people at 55 Water Street are ecstatic. We will be showcasing this like crazy, and this is the future. Now, what I'm really excited about, I call this the domino, because as soon as this one, everyone realizes what's happened, we have at least 12 mega projects in Manhattan that will also convert their existing ice storage to heating. And I just want to say thank you, NYSERDA, for being the pioneer they are. You knocked it out of the ballpark. It is truly an amazing project. We're going to see a lot more about that. Next slide. I'll skip this and let's open up for questions and answers.
Great. Thanks so much, Bruce. Let me stop sharing my screen and so I can see the chat and see if we have any questions. I don't see any questions posted in the chat. If anybody has questions, feel free to write them down. I don't think you can unmute yourselves. I have a quick question, Bruce. You mentioned Con Ed, and Con Ed was incentivizing these systems very heavily at some point. Are they still doing so? Are there still Con Ed incentives available for this? And are you, and if not, are you still seeing a big appetite for these types of projects in the downstate area, given that there are space constraints in a lot of our buildings down here for these types of projects? And what buildings do you see most well suited for this type of technology?
Okay, we're seeing this technology being embraced throughout the northern U.S. and Canada because one, it really is novel and unique, and people really are just starting to embrace decarbonization. And this is one of the few technologies that can actually make this happen. Ground source heat pumps definitely have their place. Ground source heat pumps with storage source heat pumps are really pretty attractive also. Um, and to answer your question about Con Ed, they actually provided $5.4 million for this particular project at 55 Water Street. They still have some rebates available. It's not quite as ambitious in the past, but we're going to see how that rolls out, because I do know that I believe NYSERDA had something like $67 million available for energy storage rebates. The big takeaway, if people want to get into energy storage and are looking at batteries, electric batteries are having a really hard time getting into New York City because of concerns of thermal runaway and fires. Ice storage, the worst that can happen is the tanks melt and you flood the building. Where we expect to see a lot more activity is going to be in college campuses. We think that is where we see a lot of potential as they try to figure out ways to get off of their steam system. This is a way that they can make that happen. Oh. Any further questions?
I'm not seeing any other questions in the chat, so I think we are at time, so we can leave it there. If there are any follow-up questions for Bruce, please email them to us, or feel free to reach out to Bruce directly. His contact information flashed quickly up on the screen, but we can share that with everyone who attended this webinar, if that's okay with you, Bruce. And with that, I want to say thank you very much, Bruce, for presenting. This was a very enlightening presentation, and thank you everyone for joining. We look forward to seeing you at our next showcase. And with that, have a good afternoon.
Thank you, everyone. Appreciate it.
Take care. Bye-bye.